Hello, everyone. Thank you very much for joining us today, wherever in the world you are joining us from. My name is Mike Thompson. I'm the Director of Engineering for the Verification Task Group at the Open Hardware Foundation. Um, Today, you're attending a webinar on the StarRISC MCU. StarRISC is an implementation of, excuse me, Open Hardware's CORE-V-MCU, which is an all open source dev kit, including the RTL for the RISC-V microcontroller itself, the RTL source code for the MCU, the PCBs, all the scripts to run the thing, and all the software that runs on it. These are all open source artifacts available on GitHub right now. Um, this is our third seminar on the CORE-V-MCU, and this one is really exciting for me because it goes into a completely different application domain, where we're literally talking about going into outer space. Um, so I'll let my colleagues at the University of Saskatchewan take over. I'm joined today by Dr. Chen and Christopher Elash. I'll just give you a little bit of background on both of these fine gentlemen. Uh, Dr. Chen received his PhD from the University of Alberta in Edmonton, Canada in 2004, and he's been on the faculty at the University of Saskatchewan since 2006, where he was endowed with the Barbault Chair Professorship in Information Technology. He's been promoted to associate professor and professor in 2011 and 2016, respectively. His main research interests are radiation effects and radiation tolerant microelectronics. We'll be hearing a lot about that today. He has served as the associate editor for the Microelectronics Reliability Journal, vice chair for the 2025 IEEE ICRED conference, and session chairs for 2024, 2021 IEEE NSERC conferences. He has more than 100 publications in refereed journals and conference proceedings. Dr. Chen, welcome to the webinar, and really great to have you. Christopher Elash is a PhD student reporting to Dr. Chen in electrical engineering at the University of Saskatchewan, where he studies how radiation affects semiconductor devices with a focus on single event effects in digital systems. He has hands-on experience with space system design, chip tape-outs, and I can personally attest to this last line. He has spent many hours testing electronic parts in particle accelerator facilities around the world. So that's it from me. I'm going to hand it off now to Christopher, who's got a presentation prepared for you.
Okay, awesome. Yeah, no, thanks so much, Mike. Okay, I'm gonna go ahead here and get some slides ready, and I'm really excited to kind of talk about what we have to present today. So, yeah, I think as Mike alluded to, really excited to talk about StarRISC, which is our Rad-hard implementation of the CORE-V-MCU project, and it really is a chip built from the ground up to be used in space or any high reliability environment. So I think just before I get going and start to dive into the work here, I think there's a lot of acknowledgement and a lot of shout outs I want to make to people that contributed to this project, as well as a lot of industry and agency support that helped propel this work forward. So thank you to everyone that was involved and contributed in any way to this. Yeah, just another quick background on me. I think Mike gave a great introduction. So I'm currently doing my PhD at the University of Saskatchewan here under Professor Chen, and is my hometown and my home university. I finished my undergrad degrees here as well back in 2021, and I'm studying radiation effects in microelectronics. Probably got an interest from visiting the Chernobyl exclusion zone back in, I think, in 2019. So maybe this is where the whole radiation thing started for me here. But that was a great visit. So a bit of an outline today and kind of the things that we're going to talk about. I'll kind of divide it into about 5 parts here. I think to start, we'll take a little bit of a step back and do a bit of a crash course and some background info on what radiation effects for electronics really is. Afterwards, we'll kind of talk a little bit about how there are some industry standards and common practices that we can do to protect these chips before they go off into space or any other environment that might have radiation. After that, we'll talk a little bit about how our research was then used to kind of fuel this StarRISC project. Now open source really came and saved the day and gave us a really nice platform to implement our research on. Then we'll do some nitty-gritty insights into some experimental setups and some of the results from this beamline testing that we've done on the device around the world. And then I'll wrap it all up and kind of talk about where to next. Okay, so to start things off here, so I think just like for you and me, maybe too long of exposure or too much exposure to ionizing radiation is not it's not good for us humans, and actually the same is true for electronics. So, semiconductor devices and electronics can have various effects from exposure to radiation. They can be long term or they can be short term as well. We kind of call these transient effects. That's really the focus of this talk. Um, but you can have disruptions in devices from a variety of energetic particles. So these are things like protons, neutrons, electrons. You might have heard of these galactic cosmic rays, very highly energetic particles that are flying throughout space that can strike satellites. And the single event effects that we get here from these particles, really the main concern is the change of bit values. We call these bit flips, right? So you might have a 0 change into a 1 and vice versa. And these changes in these bit values for the operation of a complex device can kind of lead to some system failures and some things that you wouldn't want to have happening while your satellite is in orbit. So, kind of some good notable examples of this occurring, throughout the past number of years here. I think there was a really popular case in Belgium in 2003 where some voting machines were adding extra votes to some candidates because of some galactic cosmic rays that had struck the atmosphere and some neutrons showered down and hit the machine just right to add some extra votes. I think there was another instance back in 2010 for, I think this was the Voyager 2 spacecraft. The flight computer crashed or stopped communicating due to a register error because of a bit flip due to some sort of energetic particle while in space. So of course, satellites in space, this is quite a common thing, but it does happen on the ground as well, shown by the voting machines. And perhaps really recently, you may have heard in the news there was some grounding of some Airbus A320s because I think Airbus was saying that in some solar events the computer could have some glitches or upsets due to increased solar activity. So I don't think they've exactly come out and said what the exact problem was, but if you read between the lines, it must be some bit flips that are occurring in the flight computers, which could cause some issues. But this applies to really any electronic device, like even like your phones, laptops. Data centers deal with this all the time. For a data center that's big enough in size, there's hundreds or thousands of bit flips occurring across all the machines per day. Industrial equipment that's monitoring some quite key things. Any of these could really fall victim to these sort of cosmic interventions. So it's sort of important that we understand exactly how this is happening, and what we could do then to prevent these issues. And this is actually really a problem that's going to get worse with time. See, as we're trying to always put more and more advanced chips with these smaller transistors into sort of every facet of our life, because the transistors are getting smaller, the likelihood of being upset by these particles kind of tends to go up over time. And not only that, but we're stuffing more and more transistors into our chips. They're getting more and more dense. As well, there's just more functionality and more things in the chip. So really, I think probably similar to new cars, more gadgets and more things inside the car. It tends to be more that can go wrong in the future. So the same applies to the chips here. If you kind of look at just a really quick physics approach as to how these bit flips occur, like what is actually happening. So if you have some transistor device like a PN junction, you have this particle that strikes the device. It leaves this ionizing track of a charge cloud. And then because there's a voltage across the device, the charge kind of gets collected and swept up into it, and that movement of charge really looks like a current pulse. So it's like you're injecting current into the device, and because there's that current pulse, you get a voltage transient, you get this glitch, and this is sort of how it's working. If you look at it at a little bit more higher level, I think maybe this will make a bit more sense. But for a digital system, that current pulse or voltage pulse can get latched into a storage latch that's storing these bits. So maybe a good way to look at it here is that on the left, this is a very common way to store bits in digital systems. This is a bistable latch. You have two inverters that are back to back, and it's stable in one of two conditions. The idea is that if you have a particle that strikes the device at the right place, it'll induce that voltage transient, and if that transient lasts long enough, then that 0 turns to a 1, and if that 1 then propagates throughout the system, it'll then flip it to its other bistable state. In that case, you've had a bit flip occur, and the data has been corrupted. So for more complex devices, moving on from a flip-flop to something that is implementing many thousands or hundreds or millions of flip-flops or registers within a device. Just a change in one bit value, you can have corrupted data. Your program can be jumping to somewhere that it really shouldn't, or just the device will halt or kind of crash altogether. So there's a variety of things that can happen. So I think moving on here, just another bit more background on, well, what can we do then to kind of prevent these events from occurring? So there's sort of a really tried and true method that a lot of industry and is still used today, to prevent systems from crashing, and that's to use redundancy in some form. So probably one of the most common ones, you may have seen this before, is triple modular redundancy. And really the way that this works is that you have a circuit, and actually you just make 3 instances of it. So they're the same circuit doing the same function. And then you attach a voter on the end to check that they're all agreeing with each other. The process kind of works like this, is that if you have an input to the system, and let's say it's a number 5, and it passes through these circuits and it does some sort of calculation, and the end result is 8. Well, because all 3 circuits are the same, you should get the same result for all of them, and then the voter checks and sees that they all agree, and it outputs 8 as the final result. If one of the circuits has an upset due to this cosmic bit flip occurring, well, your output from that circuit is no longer the correct value of 8. Maybe it's something else like 23. But because the majority of the outputs are still agreeing and they're still correct as the number 8, the voter kind of understands that, and it still sends 8 as the final output. So even though we had a bit flip occurring, we're sort of masking the result so that we can keep on operating the system reliably. But this is, quite an expensive mitigation strategy. It obviously does work, but now you're kind of triplicating the amount of area and power that you need to run the design. And there's also some architectural changes and overhead to add these voters. You might have to go back and repair circuit 1. So it does become a little bit more challenging and expensive, but it does work. And if you look at industry for people that are designing space systems that are going out, the industry offers quite a number of rad-hardened or rad-tolerant devices. I just sort of picked 3 of them here just to give a perspective as to what's out there. I mean, there's a number of them. I kind of just picked these at random. But generally, when you look at these devices, you might look at a data sheet or some sort of pamphlet. They'll give you information about the devices, and there's sort of 3 key things you're looking for. The first is a kilorad number that sort of explains, well, how long can this device survive for in space? Like how much dose can it take until it fails? They usually give a single event latch up number. That's that SEL. So that's how energetic the particle has to be until you'd get some sort of destructive event occurring. And then they gave lots of information about the clock speed and what kind of functionality there is. But there's, generally there's some issues with this across the industry, is that, a lot of the commercial devices that you could go out and buy, they're using ARM, so a bit more of a closed off instruction set architecture, compared to something that's open source and, especially increasing in popularity like RISC-V. And as well, oftentimes, data relating to the number of bit flips or crash data due to these single event effects isn't always provided, or the information around it is is maybe a little bit lacking. So as a designer, you might be wanting to ask, well, how exactly was the device hardened? Like what exactly is going on to try and make this more reliable? And then as well, when it was taken to the beamline and characterized for rad effects, what exact testing was done and how was the testing run on the device in the beamline? So some of these questions aren't always answered, but as designers, it'd be really important for us to know this. So I think moving on here and turning open source to rad hardened. So our research group has had a lot of experience and success in the past, both designing and testing these radiation tolerant circuits. And so the design process and how a project would look like that for us is that we'd be exploring, different circuit methodologies to store these bits, or to try and dampen the transients that are occurring. At the schematic level, we're trying to understand if there's some unique ways that we can, connect the transistors and devices together to mitigate these effects. And then we would go and we would implement these design methodologies into a test chip. So we'd put them into a bunch of test vehicles, so like a whole bunch of flip-flops or an SRAM array or some other structures that we could input data to and then monitor. And then at the very end of the process, we'd actually take the chip to a beamline facility, so we'd irradiate it, and then we would get characterization and a bunch of data results for all the different design methodologies that we were trying to see how effective they were. eventually we had a project that we did at the 22 nanometer node, and we actually discovered a particular methodology that was just extremely good at preventing these bit flips from occurring. I'll highlight it a little bit more here. We do have some papers that are publicly available, I think, on IEEE if you want to learn some more. But the technique is pretty simple when you look at it. So if you look at a standard latch here on the left, this is the one I was showing before for that bit flip example. You have these two inverters that are sort of back to back. At this particular node, if you do something called transistor stacking, and really what you're doing is that for the inverters, you're just kind of duplicating those NMOS and PMOS transistors. And because there's a bunch of physics going on and sort of key things that work at this particular technology node, but because the devices are electrically isolated from each other, you kind of add some distance between the drain node and then where the VDD and the VSS is connected. And the end result is that the amount of charge collected by the particles in these devices is a lot lower. So the idea is that the transient's a lot smaller, a lot shorter. The likelihood of the latch to upset from a bit flip is a lot lower. But not only do we change the schematic of the flip-flops and the way they're storing the bits, but we also do some layout-based techniques. So actually in the standard cell design, the placement of the transistors we're also modifying. For example, for a standard stacked transistor latch, you might put all the transistors kind of in a sequential order. So you'll see that there's those A1 nodes or A3 nodes are kind of right next to each other, but it's maybe not that great because if a particle hit right in between them, or a particle comes at an angle and strikes both those nodes at the same time, you could probably get a transient that's large enough to then upset the cell. So instead, we try to space some things apart. We try to interleave some of the transistors so we separate those sensitive nodes. Or sometimes even in particular, you may want to put two nodes close to each other because you get a charge canceling effect. There's all these sort of methodology and techniques you can do to change this. So after that, we also went on and we validated the technology with a TCAD modeling software. So we actually model our flip-flop cells and we look and see where the sensitive regions are within the device. There's also some other layout constructs that we may try to implement or avoid to further reduce the transient. I'm sorry if it's a little bit loud. I see there's someone snow blowing just right outside my door here. But and then we also rely on the results from our prior beamline testing to fully understand how the cells work. And so after that, we kind of come up with a finalized design methodology that we can implement for these cells. And kind of a quick comparison of them with that table at the bottom is that if we look at a standard cell that's provided from the Foundry PDK and then compare it to our hardened cells that have all these methodologies and tips and tricks baked into them, of course, you always pay some sort of price in terms of how big the cell is or how slow it is or how much power it uses to make it rad hardened. But really the key thing is that on the right there, we're talking about an LET threshold. So this is really describing how energetic of a particle do you need to strike the device before it'll upset. So for a standard cell, the value for that is somewhere around 1, whereas for our cells, it's past 120. So we kind of have like 120x improvement in the overall reliability of the cell, which is really quite bulletproof. It's really quite amazing. So with that, that methodology, we made this sort of custom standard cell library of a bunch of different flip-flops and latches and buffers. And then the thinking was that, well, we could use this library and we could make a complete rad-hardened device that doesn't have any of this redundancy. So none of that TMR with a lot of expensive penalties. It's just standard cell replacement. So we also don't have to change the architecture of a design either. We can just implement the cells and the device would still work as it was intended to by the original designers. And because we're only replacing the storage cells, the thinking then is that, well, the overall penalties on the chip of area and power should be a lot more minimal than having a full amount of redundancy. So there's quite an attractive design methodology for rad hardening. But really the thinking then was, well, what test vehicle and what should we actually use to completely validate this methodology and concept? So really we wanted to apply these cells that we made to something that had a bit of checkboxes ticked off on it. So something that was relatively complex, like a microcontroller that we could run a variety of tests on and kind of do some interesting things with. Of course, we wanted something that was open source. So you didn't want to have to pay royalties or be locked down into into something else that we couldn't play around and modify. Something that was open source, but also had some completed software tool chain, so we didn't have to spend a whole lot of time developing software ourselves. That would be a big bonus. If something came with an existing development kit board or something that we could base ours off of for our chip, so that we can connect all the peripherals up and be able to communicate with the device. Also a great thing to have. And then something finally that had support and an active community. So if you wanted to ask questions or kind of collaborate, work with someone, we could do so. And so then either by fate or luck or whatever it was, we kind of stumbled upon the CORE-V-MCU project, and this was awesome because it just ticked every box for us. It was open source, it was a full microcontroller, it had existing software and a PCB development kit with it. It was verified from Open Hardware Foundation. It was perfect. It fit our research needs exactly. So based on the CORE-V-MCU, we took the open source design, and then what we built was what we ended up calling StarRISC, which is our radiation tolerant RISC-V microcontroller device that we taped out in the 22 nanometer FDSI node. And it utilizes all those hardened cells I was talking about before in an open source design. So it is a full SoC, and this is pretty similar and true to what CORE-V-MCU is. So there's on-chip SRAM. There's a whole bunch of peripherals to communicate with the device. There are some other changes that we made, like the memory is ECC'd. There's counters in the memory, so we can see how many bit flips are occurring. As well, on the chip for clock generation, we also do have this rad-hardened PLL clock generator, and that uses some of those similar design methodologies that the standard cells are using. And it's supported by that development kit board, so it was awesome to take the open source PCB, modify, just change a few things around to fit our chip, and then we could interact with the board, pretty much almost right out of the box with some few modifications. But that was just a big help for us as well. It saved a whole bunch of time and effort. So beyond those standard cells, there's also a handful of other things that we also did and modified on the device to reduce its soft error rate or make it more rad hardened. First is the technology node that we chose. Of course, that design methodology only works at this node, but also this node is just inherently more resilient to single event effects from other nodes. The memory on board, like I said, has been protected with an ECC scheme, so it's the single error correcting and double error detecting. We have counters on board, so we can see how many of those single and double bit upsets are occurring in the memory. And we also made some alterations, so the device is always kind of reading, correcting the memory, and then writing it back in, so it's abstracted from the user. The buffer cells that are being used throughout the device, these are also FET tolerant, so they kind of reduce the amount of transients that are occurring in the device on clock or reset lines or something like that. Like I said, there's that hardened PLL clock generator, and then of course, lastly, there's all those hardened storage cells within the core and peripherals that we replaced. Okay, so moving on, I think now to some nitty-gritty experimental setups and results here. So this is kind of right where we take the device to the beamline and get some interesting data out of it. So for all the experiments that we did, we kind of had the same experimental structure in that we had the StarRISC board, and it was connected to two different things. So one was just a monitoring PC, so that we could get a whole bunch of test log data off the UART line to kind of monitor if all the tests were passing, how many upsets were occurring in the memory, information like that. And then as well, we had the device connected to the programming PC through a JTAG port, so we could load the program information onto it, and then also get some extra information in the event of a crash dumped through the JTAG. Also, the software that we ran on it during the beamline testing is maybe a little bit more unique. I think it's very common for people that when they're testing any kind of microcontroller or microprocessor design in a radiation beamline, they usually take a quite intensive ALU task like a matrix benchmark, or they do an encryption test. And so we do the same thing, but they usually just run this over and over and over again during the whole test. We wanted to look and see if there was some other things going on in the software, like looking at understanding if all the peripherals were still working, if interrupts in the device, the direct memory access controller, if all these other things are still continuing to work during the radiation test campaign. So we do it in this sort of methodology where we have the matrix test first, and then it goes on, does the next peripheral test, so on and so forth. We also run this in one of two modes. So one is a looped mode in which we run each unit test about 100 times over. or we can do it in a non-loop mode where you just run one unit test just one time, it goes on to the next, and eventually it'll come and loop back around. We also monitor all the single bit upset and double bit upset counts in the memory for these tests. Again, another big shout out for how open source kind of helped this research, and that actually a lot of the things that we wanted to test were already implemented in a CLI test that comes as an example project in the software development kit. So it was awesome to kind of take that existing software and modify it and kind of put it in the structure that we need and add some extra debugging information that we wanted to see. And so that just, again, saved us a whole lot of time and allowed us to focus on, on the research. So we had 3 different irradiation campaigns that we did with the device. I guess in 3 different countries as well, which is the neat thing. So we did proton testing, and that's at Triumph, at UBC in Vancouver. We also did heavy ion testing, so that's apologies, maybe can you still hear me, Mike? I think my headset just had a glitch. Okay, good, I'm back. Okay, good. Yeah, I think getting back on track. So we also did heavy ion testing at the Texas A&M cyclotron. So that was in Texas there. And then finally we did this microbeam testing. So that was in Australia, just outside of Sydney. So that's a really cool one. And it's also heavy ions, but we can actually steer the particles and we can kind of selectively irradiate different blocks on the device. That's something we can't do at Texas. So that was a really unique facility they have down there in Sydney. I think before we just take a look at the results, there's a whole lot of rad effects lingo that sort of the industry understands when looking at plots and talk about this kind of data. Just a quick crash course. When I'm going through it, I'll try and explain any of these acronyms and numbers that I'm talking about in a way that kind of just makes sense here. Quick recap, LET, you may have seen this before in the presentation. This is really just talking about how much energy is deposited into the silicon by one of those ionizing particles. So higher number, more energy is deposited. Cross-section is an industry term to describe, how sensitive the device is. So a bigger number, more sensitive. Flux, number of particles per second. That's sort of hitting the device. Fluence is the total amount of particles that hit it. And then there's some other common acronyms like single bit upset, double bit upset. You may have heard me say, and then as well as STEFI. So that's a single event functional interrupt, and that really just describes was there a software crash? Did the device halt, or did the software operate in some way that was really unintended? Okay, I think with that out of the way, we'll get into some results and start to look at some neat pictures and graphs here. So this was testing that was done at Triumph, so that's with those protons in Vancouver there. And so during the testing, we had a relatively small number of bit upsets occurring in the memory, about 6 per minute. That was for that non-looped and no scrub test. But we sat there for quite a while, and so it was kind of both exciting and a little bit boring in the sense that we didn't see any software failures or functional failures of the device for the whole test campaign that we were there. So, I mean, a little bit boring that we sat there and waited for something to happen, but also exciting in that we had this inkling that this thing must be really quite robust and really quite rad hard, and if we're not seeing any upsets or crashes here. Moving on then to Texas, and so this is with these heavy ion particles. So these are heavier elements that have been ionized and they're hitting the device. So they can deposit a lot more charge. They can hit with a bit bigger of a punch. So in this case, actually, now the results get a little bit more interesting. We saw that for that non-looped software testing mode that I was talking about before. We didn't see any software failures, unit test crashes, or anything up to really quite a high LET. But for that loop testing, we saw that the system would be failing at pretty much every LET that we tested at the beamline there. So it's kind of interesting. There's obviously some software dependency happening on the device in respect to its reliability. If we take a look at some results here, so on the left here, we're showing the Cepheid cross section. So that's sort of how sensitive the device is to having a software crash, as well as the double bit upset cross section. So how many double bit upsets would you be seeing? And those are uncorrectable data errors. Since for our ECC scheme, we can correct 1 bit upset, but 2 means the data is lost. Something really interesting is that typically we'd kind of expect that as the LET increases, so should the Cepheid sensitivity. It should also kind of increase in tandem, but we actually see it remains relatively flat here. That's quite interesting. And then if we look at the non-looped result, of course there is no Cepheid cross section to show, just because we didn't see any software crashes or unit test failures or anything for that software testing mode. As well, each time that it did crash during that loop testing mode, we kind of took a note as to what the device error code was. So, more often than not, almost all the time, it's this IS exception error. So this is kind of a catch-all global exception that's being raised in the device, meaning that the program counter value is going to some undefined or null value, or like when an instruction is being decoded, the instruction is not defined currently in the device, so it just kind of raises this global exception and it halts. And this is kind of true actually for most microcontroller devices when they're undergoing beamline irradiation. You kind of see this sort of result here. As well, we also saw that the likelihood of the device to fail, it was kind of more likely to fail when it was running some unit tests compared to others. That was kind of interesting. That was quite a surprise to us. We thought maybe it would have been fairly evenly split across all the different 9 unit tests that we had. By far the timers, so things related to tests for the onboard or the on-chip timers, so that might be things like the PLL or the pulse width modulation or just general purpose timers in the device. More often than not failing during those tests, and then there's some varying degree of when it fails during others. So that's also kind of a really neat thing that we saw. Kind of just a quick overview of what we talked about there. So we said that there's obviously some big software dependence on the reliability of the device. And kind of the thinking for us at that point was that, well, in that non-loop mode, we're kind of running through a lot of the device memory quite repeatedly and quite quickly. So we're kind of going through, and if there's any single bit upsets, we go through and we scrub them right away before they can turn into a double bit upset. For that loop mode, we're sort of only focusing on one small region of memory that's pertaining to just one unit test at a time. So all the other memory in the device kind of lays dormant, and it can collect these single bit upsets, quite a lot over time. And then, eventually the likelihood of you having one data word that's had, 2 or more strikes occurring in it, causing 2 or more bit flips, that tends to go up, and that's why you might see more double bit upsets, and then why the device is crashing during that software mode. Coming back to those unit tests and the likelihood of them inducing a STEFI compared to others, we tried to understand if that there's some sort of indicator based on perhaps how long the test is running for. Well, maybe. I mean, the timer test does take up a bit more time than some others, but definitely not half of the time that the device is running. We also tried to look and see if that, well, maybe it just is just taking up over half of the program space of our software. And so yeah, that timer test does take up a decent amount of space, but definitely not half. And then also, we were really looking for something to try and understand what's going on. So we were looking at the percentage of instructions as to whether for the timer test, maybe there's not as memory instructions, so the scrubbing rate for that test is a lot lower, so it could potentially get more of these uncorrectable double bit upsets. And that thinking was maybe somewhat true in the sense in that we do see that the timer test does have a smaller percentage of memory instructions compared to just other general instructions. But I mean, so too does those SPI and UART tests. So this is still just a little bit of a mystery to us, but we think it's some combination of how big the unit test size is, how often it's being accessed in the software, what the percentage of instructions are, how often it's being scrubbed. There's a whole bunch of variables that kind of go into predicting which of these unit tests might be more likely to fail. It's definitely something, still a big area of research for us and something we're kind of continuing to work on into the future. And then kind of lastly, I think just to wrap it up with that microbeam testing. So we can go and we picked a whole bunch of different functional blocks in the device. We wanted to irradiate them separately. So at that Texas facility, we kind of have to irradiate the whole chip at once. But here we can sort of selectively pick different blocks and just focus on those and only irradiate those regions. So we spent a lot of time irradiating all the individual SRAM banks, and so you actually see that there's some variation on that cross section or that sensitivity level across all the different banks. And it kind of maybe makes sense in that the software is not evenly distributed across every single SRAM bank. There's probably some pockets where there's more dense code storage than in others. This is for a relatively low LAT particle here, carbon, I think it's about 3 or 4. If we go up to something a little bit higher, I think this is around 13 or 14, we see there's a little bit more now saturation of those cross sections. The devices are becoming more sensitive, as they should, since the particle LAT is going up. You'll also see that there's all these tags here in the plots. It's called immediate CEFI. And so what that means is that we would start the program test and then turn on the beamline at about the same time. But as soon as we turn on the beamline, the device would would crash within just a few seconds. So we couldn't really reliably get all the single bit upset and double bit upset information off the memories before the device would crash. But that was quite interesting because obviously some of these blocks are really quite sensitive to inducing a software failure compared to others. So it's kind of neat that perhaps those blocks must be storing a lot more information related to the general program flow or really critical operating system information or something like this that would be causing the device to crash. We also spent some time looking at how the flux, so the number of particles that are hitting the device per second, can kind of change the relationship of the upsets that are occurring in the memory. So as the flux goes up, actually for one memory bank, this is I think SRAM bank 20, you can see that the total number of errors doesn't really go up or down depending on the flux, but the distribution of those errors as to whether or not there's single bit upsets or those uncorrectable double bit upsets, that actually does change quite significantly as the flux increases. So as it's increasing, the number of single bit upsets is kind of going down, and then most of the errors are now becoming these double bit upsets. So the particles must be hitting the device so fast that we can't go through and scrub this region of memory in time before they before those single bit upsets turn into these uncorrectable double bit upsets. I think this is highlighted really well here as well. If we irradiated the whole chip and varied that flux, we can see that the kind of time to failure decreases as the flux rate goes up, and then so too in tandem does the double bit upset cross section also go up as you increase the flux rate. So there's this inverse relationship happening here, which makes sense. And kind of one of the key things to this project is that we want to selectively irradiate each block and try to understand if we kind of come up with a more detailed failure model of the device as a whole. And this kind of really apply to any microcontroller device. I know there's a whole bunch of math on screen here, but really all this is saying is that you can take in a lot more variables than just that particle energy, that particle LET value, but you can take in the flux, how fast the device is operating, how quickly it's scrubbing through the memory, and all these different things to try and understand, what's the general Cepheid cross section of the device. You can have a more accurate number as to its reliability. And for our device, actually, this model fits really quite well with the beamline data. If we just varied one variable like the flux, we see it actually matches up like really quite well. So this is something definitely in the future you want to look at, maybe for some more non-rad-hard devices, to understand if that model also holds for other devices. Okay, there's a lot of data and a lot of interesting things that we were looking at here, but yeah, I think I'll just kind of wrap things up here quickly, and then we'll move on to the Q&A. So kind of where to next? Yeah, probably as a big summary here, I think we showed that hardening technique that we developed quite some time ago and then applied to the device, it's really effective. It makes a really exceptionally reliable device. So it worked way beyond our imaginations, and it's really a chip that's really well suited for space. One of the interesting things from our research and our projects that we showed that the software that's running on the device has a big impact on its reliability in the beamline. Kind of one thing we were kind of joking and talking about is that you should make a rad-hardened compiler, something that has perspective as to how the software is operating on the device, and instead of having to design with the rad effects in mind, perhaps a compiler can kind of handle all this scrubbing and all this different software stuff to make the device as reliable as possible. Good project maybe for a future student. Other things about like, well, if we did this again, what would we change? Where else could we go and test the device? What other experiments could we do? And as well as this, what other open source designs are there that we could use as test vehicles for other research? Obviously, it worked out so well in this case. We're thinking that there's probably a lot of other great research that could be done by using these open source designs, implementing other methodologies or other techniques in them. One of the cool things we really do have planned is that StarRISC does plan to be launched to space as a payload aboard our RadSat SK2 satellite. So that's a student-run satellite here at the University of Saskatchewan. So in orbit, again, it's kind of going to do the same thing that it did in the beamline testing. It'll run some benchmark tests and monitor its performance and reliability. So it'll be really cool to have a open hardware foundation core in space for a while. So I think that's kind of a really exciting thing. And I think, yeah, just to wrap it up here, the last slide here at the end. If you want to know anything more, of course, I think we'll have a Q&A right now, but otherwise you can always reach out to me or Professor Chen. You can check out our website at STARRLab with the QR code. And of course, always check out all the really cool projects and things that are going on at the Open Hardware Foundation. So I think with that, I think I'm done, Mike, and I hope it was an interesting presentation. And yeah, I'll be more than happy to answer any questions now.
No, I'm off mute now. There we go. Great presentation, Chris. Really enjoyed that. This is not my first time seeing these slides, but I learned something new every time. Uh, there's I just want to let everybody in the audience know if you have a question for Chris or Dr. Chen or myself, please put it in the chat. We've got a couple there now, which I can read off. One is from Marco. Straight off the bat, are you increasing the supply voltage when you
Yeah, okay.
run the StarRISC?
Yeah, good question. Yeah, so the supply voltage to, probably really any device can affect that soft error rate or that sort of cross-sectional curve. In this case, we run the device at just the nominal VDD supply voltage for this technology. But you are right that if you kind of overvolted it, you would get better soft error rate performance. And if you undervolted it, you would get worse. So for us, we run it right at the nominal voltage.
Right, the nominal voltage. Okay, cool. This is a question that's come up before, but I think it would be of interest to this audience. Is are you actually changing the the GF22 FDX PDK? So you're coming up with those stacked transistors for the
Yeah.
cells. So you're actually modifying the PDK to do that.
Well, I wouldn't say that we're modifying the PDK, but we're modifying like those standard cells that would be used in the place and route of the design. So instead of using the ones that would be provided from the PDK in a standard cell library, we're making our own. So in that case, we have our own standard cells. We have to kind of characterize them for time and information and everything. But then we're using those in the standard cell libraries that when the place and route is done, it's using our rad hardened cells instead of the kind of foundry supplied just normal standard cells. So we're not really changing the PDK. We're just changing some of the most basic building blocks of the device.
Okay, cool. A couple more questions that popped up from the in the question. I'm going to skip over the first one. We'll get back to it. Ask the second one. Is there a rule of thumb on how much radiation hardware costs in comparison to the normal hardware? So if you were to implement this MCU in the GF22 FDX without modification, how much more would it cost to implement it using your version of the PDK?
Yeah. So, in terms of cost, like you would be paying a little bit more in the sense that the total chip area would have to increase like a little bit, right? So you have to pay then for that extra die area. Um, if you're talking a little bit more from like a commercial standpoint, if you look at maybe like a space qualified rad hardened chip compared to just a consumer one, always a big price increase in the industry. Like I don't know what the modifier would be, but it could be anything from maybe like 10 to 50x depending on the complexity of the part and what it is. But yes, those space qualified rad hardened parts from industry are always much more expensive than just a consumer part you would buy from DigiKey or something.
Okay. There's another question here that I think actually I'll take. What is the difference in radiation resistance performance compared to ARM architectures? Um, what I'm going to say there is there is no specific difference because neither the ARM architecture nor the open source RISC-V architecture are specifically architected for high radiation environments. I've read ARM specs for several years, and I've read the RISC-V spec way more times than I care to mention. I can tell you there's nothing in there on either of those specs about radiation hardening devices. It's all about the physical implementation. What are the strategies that you're using? Christopher was talking about that very clever transistor stacking technique that they're exploiting in the STARRLab. So there's nothing in the actual RISC-V instruction set architecture or the ARM spec that makes one more radiation tolerant than the other. I think the reason that the STARRLab is going with the CORE-V-MCU is for no other reason than it's all open source. If you're working with ARM, ARM's got some really amazing technology, but you have to pay quite a bit of money for it. I'm not saying anything about the finances of the STARRLab, Dr. Chen, but probably it's cheaper to adopt RISC-V than it is ARM. So I don't want to put words in your mouth, but what I'm expecting is that the STARRLab adopted RISC-V simply because it was open source and the cost to adopt it was a lot less. Is that a fair statement?
Yeah, maybe I can just add one quick comment. Yeah, I totally agree with Mike, and the reason we choose RISC-V is open source, right? And we used to try to do a study version on this ARM version, and however, because education version, right, we only can access gate netlist that greatly reduce our capability to do some hardening techniques, right? And so, yeah.
Sure. Okay. Here's a really provocative question from the Q&A. It's people are start to talk about data centers in space. What's your take on that? This is probably a better question for over a couple of beers in a bar.
Yeah, I have heard this idea before, right? I think the thinking is that, well, there's more real estate in space, and then of course you have all these PV panels, and you can power the data centers without having to put a big power. I have heard this idea before. Actually, I think there are a few startups doing this. I think maybe even a few days ago I saw that someone was running some small large language model on a H100 that had been launched to orbit aboard some satellites. So there's obviously some traction to this idea, and I wouldn't be surprised if people do end up doing it. But like with that in mind, I've talked to some reliability engineers that are actually operating like data centers on the ground here, like whether those are like AWS or Cloudflare or something like this. This single event effect issue is definitely a concern for them. I think there's a really great report from Google showing that at data centers that are closer to sea level versus ones that are a little bit higher up, closer to the mountains, actually there's really quite a difference in the soft air rate they're seeing at the data centers. Just because those ones are higher up into the atmosphere, they're probably seeing a bit more particles, and so then they're getting more upsets. They usually handle them at the data centers with a lot of memory reliability and some of these redundancy techniques. But I think once you're putting it in orbit, that problem is just going to grow exponentially. And so, kind of on the rad effect side and reliability side, I think there's going to have to be a lot of work to understand how to efficiently and effectively run those data centers while keeping them reliable and having that 5 nines of uptime.
Excellent. Here's a question that I didn't anticipate at all. On the software side, there's a huge push for Linux in space with compatible hardware, and there's a link that was provided. I think everybody can get to it. I'm going to save that link and pass it along. Question is, are you guys looking for collaboration on that front?
Yeah, I think of course, yeah, we're always looking for interesting, unique collaboration. Yeah, as for Linux in space, I think that definitely is growing and becoming more popular. Actually, I think our student design satellite is running some sort of distilled version of even Ubuntu or some version of Linux actually on the satellite as the operating system on board. So yeah, definitely becoming a lot more popular. It's interesting, easier for development, and yeah, that's interesting. The collaboration on that front, I think, could be a unique thing. So we should maybe get in touch.
Yeah, absolutely. I mean, I'm just looking at the link that was provided right now, and it's a keynote address at the Open Source Summit in Japan. It just ended yesterday, and the title is "Space Grade Linux: Building Safer Open Source Future for Space Systems." So that's an exciting idea. Space grade Linux.
That is a great idea. Yeah, especially because I think this Linux is more like from a design perspective of people writing software. Embedded C and different things like this, not maybe as many people are well versed in that, but just for general Linux development and if you're running Python or whatever it is that's more
Yeah.
accessible with
Yeah.
Linux, makes sense. Yeah.
Well, I think some of your results sort of hint to that there's a role for software to play in this. There certainly seems to be a sensitivity And that's I'd have to talk with you and Dr. Chen about that one offline, because it's got the juices going on that one. That's interesting.
Okay, good.
Just so that everybody's aware, the CORE-V-MCU that StarRISC is based on, it is an embedded controller, so it's not designed to run Linux or Linux applications. The operating system that runs on there, and I'm pretty sure StarRISC is using this, it's an implementation of FreeRTOS, which itself is an open source artifact.
Yep, that's right.
Yeah. Okay. Well, that's it for the questions in the queue. I think maybe, let's see, we've got 7 more minutes till the top of the hour. I don't know if we need to wait anymore. If there were any other questions coming, I think they'd be here. I want to thank Christopher Elash for that great presentation, and Dr. Chen for his leadership in the StarRISC project. It's really, really exciting. I'm super excited to see this darn thing go into space. So this is going to be really cool. It will not be the first RISC-V processor in space. There's one that a European lab just sent to space literally last week. And
Yeah.
there's another one that was done by an American company last year. So, but I think there's going to be a lot of RISC-V in space, and your approach, your very novel approach to creating highly effective yet low cost, radiation hardened implementations is going to attract a lot of attention.
Yeah, definitely. And yeah, even the new next generation NASA high performance space computers, those are RISC-V based. So that was really cool to see that.
Yes,
Quite a big agency and government organization was moving to RISC-V for their compute, and then putting that in space. That was, yeah, really validating and really cool to see that.
absolutely. All right. Well, I guess we can wrap it up there. There's no more further questions, and I want to thank everybody who attended. This video will be available on YouTube in a couple of weeks. It's going to go into post production, so we can get rid of all the coughing that I did. And but we'll definitely promote, on all of our social channels. We'll promote the location of this on YouTube. And like I say, this is the 3rd video on the CORE-V-MCU. While you're there, go check out the first 2. All right.
Okay.
Okay. Awesome.
Thank
Thanks
you,
so much.
everyone. All right.
Hey.